In the last lecture, we discussed feedbacks in the Earth climate system. We talked about water vapor changes, lapse rate changes, and changes due to melting of ice and snow. I also mentioned briefly the cloud feedback. The cloud feedback is the most important feedback, and it is the one in which there is largest uncertainty because it is very complex. Because clouds come in many forms, and different kinds of clouds have different feedbacks. Okay? So, more than 45 years ago, the National Research Council had a report published by Jules Charny, a well-known climate scientist, who said that modeling of clouds is one of the weakest links in the general circulation modeling efforts of the climate system. Now, even after 45 years, although our knowledge has improved a lot, we still have lots of challenges because clouds are extremely complex phenomena. Now, let us have a brief understanding of how clouds influence the Earth system. We all know that clouds reflect radiation from the sun, and that contributes to the planetary albedo of 30%, 0.3, okay, which we discussed a lot. Now, the planetary albedo that we discussed is coming both from cloudy sky and clear sky. Okay. So, approximately the fraction of clouds, global mean fraction, is around 60%. Clear sky is about 40%, and the cloudy sky has an albedo around 40%, 0.4, while the clear sky has albedo of only 15%, 0.15, because clear sky mostly is ocean and some land. So, it has much lower albedo or reflectivity than the cloudy sky. So, if you take these mean values, these are rounded off for convenience. So, we get the planetary albedo as 0.6 into 0.4 is 0.24, and 0.4 into 0.4 is 0.16. So, we get 30%. Okay. Now, you look at the data from satellites, okay, about the radiative fluxes as measured by them. If we look at the average value, which we mentioned, outgoing long wave radiation is about 234 watts per meter squared. Absorbed solar is around 239. They should exactly balance, but on account of errors in measurement, there is a 5 watts per meter squared, what you might call is error or residue. Okay? And the albedo, as we mentioned, is around 30%. Now, if you separate out the cloudy region from the cloud free region, in the cloud free region, satellites indicate a much higher radiation, which is not surprising because clouds being at a level higher than the Earth's surface, they will emit less radiation to space than the cloud free regions. So, it is around 31 to 32 watts per meter squared more. Okay. This difference is called cloud forcing. So, the clouds being there reduce the outgoing long wave radiation by around 31 to 32 watts per meter squared. Then look at absorbed solar. In a clear region, more radiation is absorbed by the ocean, okay, while in the total Earth with clouds, there is less radiation absorbed because cloud reflects out the radiation. So, this difference is around 48, 49, and so this shows clearly that the presence of clouds in the Earth's atmosphere causes cooling, while the presence of clouds in the long wave causes warming. If you take a sum of these two, cloud causes net cooling. So, cloud causes warming in the long wave, cloud causes cooling in the short wave. The cooling in the short wave is larger than warming in the long wave. So, the sum is the net cooling. The presence of clouds in the Earth has reduced the heat flux by 17 watts a meter square. If you compare the albedo of the cloud free region compared to planetary albedo, it is difference of 15%. So, cloud changes the albedo by around 15%. So, that is to be understood. Now, why do clouds do that? To understand that, you must look at models which calculate the reflectivity in the short wave region as a function of total liquid along the path. You integrate liquid droplets from the surface to the top of the atmosphere, and you get the values in grams per square meter. Okay. So, when there are not many liquid droplets, around 10, depending on the droplet radius, okay, you may get either, if you have a small droplet, you have a large reflectivity. If you have a large droplet, you have a low reflectivity. So, small droplets reflect more. Okay. And as the amount of liquid increases, the reflection increases and reaches an asymptote for a large liquid water path of around, depending on droplet radius, around 70%. On this side, you see the same thing plotted a function of concentration of cloud droplets. Okay. This is the liquid water path, this is number cloud droplets, and then you have to mention what is the cloud thickness to get the total amount of liquid water. And so, this shows a slightly different picture because it shows the role of cloud drop concentration and cloud thickness, while this combines these two in terms of liquid water path. Okay. So, what this shows is both the cloud droplet size and the cloud concentration have an impact on albedo of the clouds. Now, a long time back, people examined why different models give a different climate sensitivity. Okay. And so, they compared the clear sky in the model with the total sky in the model, and they showed that clear sky, top of the atmosphere, net radiation agree well among models, but total sky do not agree. It shows clearly that the difference between different models is mainly due to clouds. Under clear sky condition, models show the same amount of greenhouse effect and the same amount of albedo changes in different models, but as soon as you go to all sky, that is clear sky and cloudy sky together, there is a large difference. So, this shows that clouds in different models are very different. They have different reflectivity and different greenhouse effect, and they cause a large differences. And so, after this work of Sess et al. In 1989, a lot of observation and modeling effort was done to see how to reduce the difference between different models because of the way they model clouds. Because cloud, as I mentioned earlier, is not put in there in the model from first principles. There are approximations made because models do not really resolve the cloud. The cloud is typically 1 kilometer in size. The model grid size is typically 50 by 50 kilometers. So, they cannot really simulate each individual cloud from first principles. So, they use an empirical relationship between relative humidity and clouds, and that is not same in all the models. Okay. And the models use empirical data from observation based in various countries. So, each country uses a different empirical data, and so they differ in their results. Now, the reason why you have to worry about it, that if carbon dioxide caused a net radiation change of 1.6 watt a meter squared, then a 3% change in the reflectivity of solar radiation by clouds, or a 5% change in reduction of the outgoing long wave radiation will counteract that 1.6. So, it requires a very small change in the cloud fraction, 3 to 5%, to change the net radiant top of the atmosphere equivalent to what happens due to CO2. And between different models, the change in cloud fraction is quite large, and that is why different models are not agreeing on the impact of clouds. Now, why is that? Now, if you look at clouds in the atmosphere, they come in a variety of forms. Here we have just merely given an example about 7 or 8 types, but in reality there are many more, but we make life easy. The one which of interest in India is a large cumulonimbus clouds, which starts from around 1 kilometer above the surface all the way to 12 to 13 kilometers. These are the ones which bring lots of copious rain during the Indian monsoon. You also have small cumulus clouds which are located at the height of 2 to 3 kilometers. They do not rain much, but they have an impact on cloud albedo. Then you have the cirrus clouds which are at high altitude. They are ice clouds, and they trap S radiation quite well. They do not reflect much because their reflectivity is not high, because ice crystals reflect much less than water droplets. Okay. So, that is a big difference. And then we have low level raining cloud called nimbostratus, and there are clouds slightly higher level which are called stratocumulus. They do not rain much. And then you have cumulus clouds which are vertically varying with height, while cirrus appears on one height. This varies various heights, and this also traps the Earth's radiation. And there are stratus clouds, plenty of them, low level clouds, which cause a large change in albedo. So, a climate model has to reproduce these different clouds correctly in order to get the albedo at the top of the atmosphere, and with increase in CO2 they have to correctly simulate the change in albedo and greenhouse effect. So, there are many kinds of models. So, with satellite data being available, it was decided to simplify all the complex clouds we have on Earth to 9 different types based on how thick the clouds are. This is defined by cloud optical thickness, which is the logarithm of the incoming radiation to what is transmitted. The denominator is lower than the numerator. So, this is a quantity above 1. So, log will be a positive quantity. So, if the cloud optical thickness is large, which means the cloud is absorbing or scattering a lot of radiation, while if it is small, it is not absorb or scatter radiation. So, this is one parameter, how thick the cloud is. The second parameter is how high the cloud is, how far high the cloud goes up in the atmosphere. If the cloud top is very high, let us say 180 millibars, then those are mostly cirrus clouds or cirrostratus, or this cumulonimbus clouds we showed in the last slide, which is a deep cloud, cumulonimbus, and so they also have ice at the top. So, all these are clouds with ice in them, and so they are about 6 kilometers in the atmosphere. Then there are middle level clouds, altocumulus, altostratus and nimbostratus. Of these are the ones which cause rainfall. These do not cause rainfall, but they have an impact on the radiation budget. Then we come to clouds in the boundary layer of the atmosphere, the lowest 3 kilometers. We have cumulus clouds, stratocumulus and stratus. These alter the Earth's albedo and have an impact on albedo of the Earth. Now, if you look at the data from satellite, the International Satellite Cloud Climatology Project, which has been running for the last 40 years, based on many satellites going around the world, and they show the cloud variation in different parts of the world, okay, and various kinds of clouds, and we look at how these clouds alter the cloud emissivity and cloud albedo simultaneously. We looked at it separately. Now, I want to look at it simultaneously. As the cloud liquid water path in grams per meter squared increases, both albedo and emissivity go up. There is more liquid water and ice in the column, so they will reflect and they will absorb more radiation. So, both emissivity and albedo goes up, but note that emissivity goes up much faster than the albedo. So, by the time we come to 100 grams per square meter, emissivity is also almost 1. So, cloud behaves like a black body. But at that point, the cloud albedo is only around 0.5, only reflects 50% radiation. So, in the visible, the cloud does not behave like a black body, but in the infrared, where we calculate emissivity, is almost 1. So, this big difference in the behavior of the cloud between the infrared and the visible short wave should be clearly understood. So, cloud's behavior in the solar short wave region compared to Earth long wave region is very different. It is similar to the gases. Gases like CO2, water vapor are almost clear in the short wave, but highly absorbing in the long wave. Cloud has a similar behavior. In the long wave, it absorbs a lot of radiation and hence emits more, but reflection is more in the visible region than in the infrared. Now, let us compare how different climate models simulate clouds. Okay. So, I have compared the high clouds, cirrus, cirrostratus and deep cumulus clouds, and altocumulus, altostratus, nimbostratus, cumulus, stratocumulus and stratus, all the different kind of clouds we showed in the last slide, and the percentage of these clouds, okay, at different heights. The two black lines here indicate the observation. There are two major satellite data available: International Satellite Cloud Climatology Project and CERES, which I discussed earlier. So, both these provide data on various clouds, and you can see that they do not agree perfectly. For example, for cumulus clouds, ISCAP says 10%, CERES said 13%. Now, this is partly a sampling issue. ISCAP has better samples in the tropics because it uses geostationary satellites, well CERES does not use that many. So, there will be some difference because of sampling of the clouds, and the same problem with middle clouds and high clouds. The middle and high clouds, CERES shows less clouds than ISCAP. Okay. But you see that in the case of thicker clouds, the agreement is not too bad. Okay. The problems only comes in optically thin clouds between the satellite data. But if you look at the models, there is a huge variation. Let us look at cirrus clouds. There are some models showing hardly 5%, there are models showing 20%, while the mean of these two is around 10%. So, only 3 or 4 models correctly get 10%. Some models get too high, some get too low. In the case of cirrostratus, you can see that most models are okay compared to satellite data, which are in good agreement, but one model shows too high cirrostratus. In the case of deep cumulus cloud, there is a huge problem. Satellites say it is around 3%, while model average is around 6%. So, this is a huge problem, needs to be understood why they are not doing well. When you come to alto-cumulus, same problem, satellites show around 6% while models are showing 1%. Serious problem. Same with altostratus. I would say nimbostratus not too bad. If you take a mean of all this, it will roughly come to 2%. If you come to low level clouds, there is some problem with cumulus clouds, but stratocumulus is not bad between models and observation. And in the case of stratus clouds, models are estimating too high a cloud fraction compared to observation. So, generally you see that situation about simulation of clouds by climate models is not satisfactory. Now, this is in spite of 40 years of serious research work done all over the world. We have not improved, partly because climate models are not able to resolve clouds well. So, this is bound to improve in the next 10 years as models get to a higher resolution. Now, models are going to come with a resolution of 10 by 10 kilometers. So, that will definitely improve the situation, but right now this is the state of the art and we have to accept the limitations. Okay. Now, I am comparing one model's simulation and this model is community atmospheric model from the group in NCAR in Boulder, Colorado, and here is an attempt to compare how cloud fraction varies low, middle and high with latitude for ESCAP and Ceres, which are in red and here light pink color, and model is in green. Okay. First problem, you can see that CAM2 has a tendency to have too high a cloud, more like in the tropics more like 45%, while satellites show 25%. This is a huge problem. This model has to improve. On the other hand, you look at middle clouds, middle level clouds, the model comes in between satellite, two different satellite measurements. So, if you assume that the actual data is an arithmetic average of two satellite data, I would say that the middle level clouds agree quite well with model simulations. Finally, we come to low level clouds. Because low level clouds, the models agree with satellite data of ESCAP quite well between 40 south and 40 north, but the two climate satellite observations, they do not agree, unfortunately. But at high latitude there is a problem. At the high latitude, the model tends to predict too high a cloud fraction, which neither of the satellite data reproduce. So, this gives an idea of fairly serious problems in the tropics with reference to high clouds, and in the case of low clouds, the models are having problems of giving a too high a cloud fraction at higher latitudes. So, these two have to be corrected in order to get good results. Now, here is a comparison of cloud fraction by 25 different models with two different satellite data here, three different satellite data. Okay. So, satellite data show a mean cloud fraction of all clouds of around 55%. Okay. And I would say most models are getting it right except one or two models. So, most models get the global mean cloud fraction almost close to the satellite observation within the error in satellite measurements. So, as far as global mean cloud fraction concerned, we are doing well, but if we look at tropics and polar regions separately, the models are not doing that well, and if you compare low clouds and high clouds, models are doing well, but if you take an average of all low and high clouds and between tropics and mid latitudes, a global average, then we are doing okay. Now, here is a comparison between an atmospheric model intercomparison project, where they specify the sea surface temperature and run only the atmospheric model and look at cloud fraction over a period of 20-30 years. And then they also run a coupled model, where the atmospheric model is coupled to an ocean model. So, sea surface temperature is calculated, not specified. And you see that the difference between coupled and atmospheric model is not very different. Global mean error in cloud fraction. So, models tend to have a lower cloud fraction. They will have them whether it is coupled or not coupled. So, in the set that is shown here, I would say 1, 2, 3, 4 models slightly over predict the cloud fraction, while about 6 models under predict. Okay. And so, this is state of the art. So, this you have to accept, but remember, a 10% error in the global mean cloud fraction is not acceptable, because we saw in the earlier slide a 10% error in cloud fraction will lead to a huge error when compared to impact of CO2. If the cloud fraction is in error by 10%, you cannot be confident about that model's ability to predict what will happen due to increase in CO2. So, this is a challenge that is being faced by the climate modeling community, that their modeling of clouds is not sufficiently accurate, that they cannot with great confidence predict what will happen due to global warming induced by a CO2 increase. So, this is a fact all of you must appreciate, and remember that future climate predictions will have some error because of the model's errors in their simulation of cloud fraction. Now, sometimes this is taken to imply that we do not have to trust models. That is not the right interpretation. Because models are not able to predict clouds correctly, there is some error in our prediction of the future climate. But remember, the error is on both sides. Either they will predict too high temperature or too low. So, because of that uncertainty, you cannot say I will not look at climate models. That uncertainty implies that we need to be more cautious. That means the real impact of CO2 may be worse than what the model predicts, not necessarily better. So, this is a fact that many people do not understand. They must realize that model uncertainty implies that we need to be more careful and more cautious in our attempt to control carbon dioxide. Okay. Now, here is a simple chart showing how the impact of the model in the visible, where it alters the planetary albedo, and the impact of the model in the infrared, where it affects the amount of radiation emitted to space, they go in the opposite direction. When clouds form, they reduce the outgoing log wave radiation, because clouds form, the radiation emitted to space is blocked by the clouds. Cloud has a very powerful greenhouse effect. Okay. At the same time, cloud alter the albedo. Whether the albedo effect is more or the greenhouse effect is more depends on the relative change in albedo, relative change in cloud top altitude. So, there is one particular line along which they exactly cancel out. Okay. The effect in the visible short wave and the effect in the long wave. But some models will be on this side, some will be on this side. So, that alters the how much global warming the model predicts. If the models effect in the long wave and the short wave exactly cancel out, then life is very simple. Okay. But we do not think it happens in real world. So, this is a challenge that we do not know in the actual data whether the effect of change in clouds, the long wave and the short wave effect, do they mutually cancel out? If they do, life will be simple for us. We do not know. So, since different models show different levels of cancellation, we have to be little careful about our future predictions. Okay. So, let me summarize this. On account of the decrease of temperature of the altitude in the troposphere, higher clouds are colder and thus emit less thermal radiation to space. Therefore, an increase in altitude of the cloud top imparts a heating to the climate system by reducing the outgoing long wave radiation. This is a higher greenhouse effect. Okay. The rise of upper level cloud top heights is based in very good theory, okay, and is supported by cloud resolving experiments and by observation of both interannual cloud variability and multi-decadal trends. So, as the cloud warming occurs, the isotherms are supposed to rise. So, the cloud tops cause a positive cloud albedo feedback. Okay. And so, this confirms the assumption that the cloud top temperature will be somewhat fixed. Okay. It is a more realistic assumption in response to warming of the earth. So, the radiative impact of clouds as measured by cloud radiative effect, that is the difference between clear sky and all sky, from satellite measurement shows a value of minus 45 watts per meter squared, while the reduction in the outgoing long wave radiation is 27 watts per meter squared. If you add these two, you get minus 18 watts per meter squared. So, at the present climate, the clouds are cooling the earth to the tune of 18 watts per meter squared. This is quite large. Okay. And so, this must be kept in mind that in the present climate, clouds are causing cooling, but we are not sure about what will happen in the future as the CO2 increase alters the clouds. As the CO2 increase alters the clouds, either due to change in cloud fraction or change in cloud height or change in cloud albedo, the temperature can either increase or decrease due to the effect of clouds. And so, this is an issue which we do not fully understand today, and so we must be cautious about believing the simulation of these global climate models, because they do not simulate change at present accurately. Okay. So, with that I will come to the close of this lecture and will continue this discussion in the next lecture.